Hi everyone, and welcome to this first lesson on probability theory. The first thing I want to point out to you is that in some of your classes, you're going to start with permutations and combinations and counting techniques. These are useful for making interesting problems in probability theory, but they're not really probability. They actually fall in a branch of math called combinatorics. And if that's what you're learning, follow this link here to learn more about combinatorics. For our lesson, we're going to start off with basic terms and definitions in probability theory. So in a probability, we have some kind of experiment, such as flipping a coin or rolling a die, and those experiments have outcomes. So if I flip a coin, the outcomes are heads or tails. And if I roll a die, the outcomes are 1, 2, 3, 4, 5, or 6. The set of all possible outcomes is called the sample space, and we represent that by omega, which is this Greek letter here. There are also subsets of omega, which we call events, and those are the sets that we can measure the probability of whether or not they occur. The set of all measurable events is called the event space, and is denoted here with the script E. We won't spend too much time talking about the event space in this course. It's usually talked about more in a graduate level course, but we should at least point out what it is and some of the properties of an event space. So the event space, a lot of these properties are going to depend on certain definitions from set theory. So if you're not familiar with set theory, you should definitely go over and check out those lessons. Here's some links to the notation we're using. So if there's any particular thing you're not familiar with, you can go directly to that lesson and learn about that. So first of all, the event space is a subset of the power set of the sample space, just meaning that every event is a subset of the sample space. The entire sample space is an event itself. So we always know that the sample space does occur because it's all possible outcomes. So if we run an experiment, we get one of the possible outcomes. If A is an event, then so is its complement. That is, if I can tell whether A occurs, I can also tell whether it doesn't occur. And likewise, if I know the probability that A is going to occur, I also know the probability that it won't occur. The last point is that the union of a countable set of elements in E is also in E. So if A1, A2, A3, and so on are all events, then the union of all the A's is an event. This just means if I know whether A1 occurs or not, whether A2 occurs or not, and so on, then I also know whether at least one of the AI's occurred. So that's all we're going to talk about the event space. And now we'll get into something more important. Let's talk about the definition of what a probability is. So a probability is just a measure that measures events between 0 and 1. The notation for a probability will be a capital P. So that is, the probability is a function, and it takes an event and maps it to 0, 1. Usually that map will tell us what the likelihood of that event occurring is. So remember, the sample space is an event. That means there's a probability for the sample space. And the probability for the sample space is 1, because we know the sample space will always occur, since it's all possible outcomes. And this third bullet looks more complicated than it probably is. So if we have A1, A2, and so on, are a collection of disjoint events. So disjoint is important here. It doesn't work for any collection of events. And by disjoint, we mean that the intersections are empty. Then the probability that at least one of the events occurs is the sum of the probabilities of the events occurring. This isn't just true for infinite sets. So we could replace the tail end of the sets with a bunch of empty sets. So that also is true for finite collections of sets. And I can write down an example here on the space we have on the chalkboard. So let's say that we have two events, A and B, and that their intersection is empty. So A intersect B is an empty set. Then the probability of A union B is equal to the probability of A, writing kind of thin here, plus the probability of B. So that's what this means for two sets. That might be a little bit easier to see. We'll also talk about it down here in this example. So let's look at an example for a probability. Let's say you work at a company that sells two products. There's a cheap product and an expensive product. And your job will depend on what the result is of a sales team when they try to sell to a customer. If the sales team sells an expensive product to a customer, you need to send a thank you letter to the customer. If the sales team sells a cheap product to the customer, you'll still send a thank you to the customer, but the thank you will also include a reminder of the benefits of the more expensive product. So you're going to upsell in this letter. If the sales team does not make a sale, but the customer did express interest in the products, then there's going to be a different team that follows up. So you won't have to do anything in this case. And I just noticed here that I have 2 periods, so please ignore one of these periods. I'll probably have that fixed on the site pretty soon, by the time you're seeing the video. But finally, if the customer was not interested in any of the products, they're going to be left alone. So they indicated that they aren't interested and you won't bother them. So in the cases of C or D, you don't have to do anything. There are roughly 10 sales pitches a day, 2 of which usually have a result of A, and about 5 times you'll get a result of B. So 7 out of 10 times you have to do something. Now a customer is about to meet with the sales team, and you want to represent the likelihood that you'll have to do job A or job B with a probability. There are 4 outcomes that make up the sample space. The sample space is A, B, C, or D. The customer is going to do one of those 4 things. You can only measure the outcomes of states A and B. If C or D happens, you don't have to do anything, so you don't actually know what happened. Maybe the customer expressed interest, or maybe they were totally disinterested in the products. So you don't know exactly if C or D happened. So the event space would include the set A, because you'll certainly know if that happens, and the set B, and then the set with C and D combined, because you'll know whether or not the event of C or D happened, because you won't do anything. But you can't get a finer partition than that, so you don't know about C itself or D itself. So that takes care of these first sets and the event space. But also you can combine these, right? So you'll know whether or not A or B happened. You'll know whether A or C or D happened, whether B or C or D happened, whether something happened over here, that's the sample space. You always know one of those things happened, and whether none of those things happened. So the empty set is always in the event space as well. That's the event that nothing in the sample space happened, which always has probability 0. So the sample space has probability 1, something always happens in the sample space, and the empty set is something in the sample space that doesn't happen, which has probability 0. Okay, a few of these we can immediately assign a probability to. So the probability that A happens is about 2 out of 10, because you've noticed over time that roughly 2 out of the 10 customers every day buy the more expensive product, and you have to do job A. B has a probability of about 5 out of 10, because you've noticed that over time. And then C or D, the event that you don't do anything, has a probability of roughly 3 out of 10. Then with this information, you can find the probability of any event in the sample space. So if you look at the probability of ACD, which is one of the events in the sample space, you can compute this by using the rules of probability. First, the probability of ACD is the probability of A union the probability of CD. So we can break this into 2 sets, the set just containing A and the set containing CD, because we know, just a little bit above here, the probability of A is 2 out of 10, and the probability of CD is 3 out of 10. So we can use these 2 sets. Now these are disjoint, right? Meaning that the set containing A intersect the set containing CD is empty, right? There's no overlap between A and CD. And therefore we can use the property of probability, that the union of the sets is the sum of the probabilities. So the probability of A union CD is the probability of A plus the probability of CD. Then we plug in these numbers. So the probability of A is 2/10, the probability of CD is 3/10, right, listed up here. And 2/10 and 3/10 give us 5/10 or 1/2. So the probability of A, C, or D happening is 1/2. And then down here, there's a quiz as usual, so you can use this quiz to check your understanding and make sure you did understand the fundamental definition of probability. See you all in the next video.